Okay, we had considered so far basically three important tests to determine divergence or convergence of series with non-negative terms, or at least which are ultimately non-negative. Now, if a series is not ultimately non-negative, which is the same thing as saying that it is ultimately non-positive, because by taking a minus sign out, we can deal with them in the same way. Okay. This means that there are infinitely many positive and negative terms. Okay. Then, the above tests are not applicable in the first place. With the exception of the nth term test, obviously. Okay. Now, what can we do in such cases? Well, in general, it can be very difficult to determine convergence or divergence of such series. Okay. In general, then, it is not easy. It can be difficult or even to determine their convergence, divergence. Okay. But a partial solution is the following. To the problem is the so-called absolute convergence theorem. Okay. It's a nice theorem in the sense that its statement is easy and the argument behind it is also easy. Namely, it says that if the absolute value of ANs add up to a convergent series, then without the absolute value, the series is also convergent. Sorry, I should have said convergent. Is also convergent. So this solves the problem of a series with a lot of negative and positive terms in the following sense. When we put absolute value, we have a series with non-negative terms. So if it is convergent, then the original one is convergent. Okay. But it doesn't give us a complete solution, because if with absolute value the series diverges, it says nothing. Okay. The proof is quite easy if we look at the partial sum sequences. Okay, let an be the partial sum sequence of ans, and let bn be the partial sum sequence of absolute ans, and let cn be the partial sum sequence of absolute an plus an. Now, of these, the question is, does limit of an exist? We know limit of bn exists because we have a convergent series here. So here we know limit bn exists. Okay. It's the hypothesis. So let me say by hypothesis. Now, let us consider Cn. Okay. First of all, when we look at an plus an, we observe that it's always positive. In fact, if you add the absolute value of any real number to itself, okay, you either get a positive number or 0. Okay. Then we have a comparison. This is always true. It says that Cn, which is non-negative, is bounded by 2 times Bn. Okay. Well, we know something else about Cn's. Because in Cn, these are all positive, okay, Cn increases. You're adding non-negative numbers, so you get a larger and larger number, or the same number if you're adding zeros. Now, here we know that limit of Bn exists, but Bn is also increasing. Because Bn is increasing, this is true. That is, if you have an increasing sequence and if it has a limit, its limit is bigger than all terms because you continue adding positive numbers to it. Now, okay, this is because here Bn is increasing. Okay. Now this says that Cn as a sequence of partial sums given here, okay, is increasing and bounded. So limit of Cn, let us call it L1, exists. Now, this solves our problem, because if we look at an now, it is Cn minus Bn for every n. Okay. These are finite sums, so we can do such operations. So, when n goes to infinity, this approaches L1 minus L. So, okay, the series of an converges. Okay, now let us consider some examples. To apply this. Well, let us consider a series where we have sine n over n squared. Now, sine n, when n changes in positive integers, has a lot of positive and negative values, infinitely many. Okay. So, this an is not positive or negative all the time. Okay. So here, cis an, that is sine n over n squared, okay, is not positive or negative all the time. Or rather, ultimately, let me say. Okay. We cannot use any of the previous theorems. So, previous theorems cannot be used. Okay. So consider absolute A. Now, obviously, absolute an is non-negative for every n, and it is bounded by 1 over n squared, obviously. But then, since the P series with 2 is convergent, P is bigger than 1, by comparison theorem, or test, the series with absolute an is convergent. Now this says, by absolute convergence theorem, okay, that was the name we gave to it, by absolute convergence theorem, okay, the series without absolute value also converges. Okay. So this is a convergent series. Okay. As a second example, let us consider this so-called alternating harmonic series. Now, clearly, because of the term -1 to the n here, the terms go positive, negative, so it's not ultimately positive or ultimately negative. There are infinitely many positive and negative terms. So we try to look at the absolute value, which of course is the harmonic series, which is divergent. Okay. It's a P series with 1. Now, this tells us that absolute convergence theorem says nothing. Because it says something only if the absolute value version is convergent. Okay. So it doesn't work. Now, what can we do about it? Well, at this point, we will not do much, okay? But by the next theorem to be proven, okay, this series happens to be convergent. But as I said, we will show it later. Okay. On the other hand, we can also consider minus 1 to the n plus 1 over n squared. Okay. Now this series, okay, fine, is again not a ultimately positive or ultimately negative series. So we consider the absolute value. Okay, which is the series 1 over n squared, which happens to be convergent because p is greater than 1. Okay, so by absolute convergence theorem, the original one is also convergent. Well, now as promised, let us state and prove a theorem which will say that the second one is convergent as well. This is the so-called alternating series theorem. Usually called a test. Okay. It is attributed to the German mathematician in the 18th century, Leibniz. Okay. It says the following: if a series satisfies the three conditions. Okay. Firstly, it is alternating. Okay. An alternating series means that it changes its sign. Okay. At each term. Equivalently, it means that an times an plus 1 is strictly negative for every n. There are no zero terms in this series. Okay. 2, okay, the absolute value of an decreases. And finally, limit of absolute value of an is 0. Then the series is convergent. Okay, so this is a special case where we have infinitely many positive and negative terms, okay, but under very strict conditions that the absolute value term decreases to 0 and the signs change at each step. Okay. Now the proof of this theorem can be done quite easily. The point is that we can represent an as absolute an, which I will call Bn, times minus 1 to the n, depending on n, it doesn't matter much. One shift by minus 1 is possible. That is, it might be multiplied by minus 1. That's not the point. The proof we will do for this will be the same as the other one. Of course, we know Bn is a decreasing sequence, and it goes to 0. Okay. So we look at S2n. That's the sum n 1 to infinity, okay, minus 1 to the n Bn. This is, remember, our an. Oh, sorry, up to 2n. Now, this obviously is the following. For 1, you have minus B1, and then you have plus B2, and then minus B3 plus B4, and it continues like that. Finally, you have B2n minus 1 plus B2n. Okay. Now, in this sum, okay, we see that this sequence up to B2n has a limit. Why is that? Well, let us look at this sum more carefully. Okay. B2 minus B1, because B is decreasing, okay, is negative. Actually, all of them are negative in this case, because always this term is smaller than this one. So all pairs here are all negative numbers in the first place. So this is negative as a whole. On the other hand, every time we are adding, when n increases, a term which is negative. Okay, so okay, we add okay, negative terms, or rather non-positive terms. So, okay, our S2n is decreasing with n. Now, to show that it has a limit, we only have to show that it is bounded from below. Okay? So, let us look at S2n from a different point of view. That is to say, okay, let us, all of these are negative, all these pairs are negative. Okay? So we want to make it even smaller as follows. This should be, now we can write S2n as follows. It's minus B1, okay, plus B2 minus B3. Now let us look at this pairing. That would be, okay, positive. Because B is a decreasing sequence, and so B3 is smaller than B2. Similarly, continuing there that way, okay, we have B4 minus B5. This is likewise positive, and so on. Okay, the pairing would give us positive terms, and except the final term, B2n. These would be all positive. So this is greater than minus B1 plus B2n. Well, here B2n goes to 0. Okay, so it is in absolute value greater than some number eventually. Thus, this tells us that we have minus B1 okay, which is a positive number, and plus, okay, say 1, rather minus 1. Here the idea is the following. Limit b to n is 0. So for epsilon 1, okay, b to n, and 0 minus this would be less than, okay, 1 if n is greater than some and 0. Okay. Right. Now this, of course, says that, okay, minus b to n is less than 1, or minus 1 is less than b to n if n is large. Okay. So we obtain S2n is greater than, okay, minus b1 minus 1 if n is large. But then there are only finitely many left, and this says that, so S2n is bounded from below. So it converges. Okay. It's a decreasing sequence with a lower bound, so the limit exists. Okay, but then, okay, if we look at S2n plus 1, it is S2n plus, okay, minus 1 to the n, actually 2n plus 1, b to n plus 1. Now at this point, okay, this S2n goes to an L. This term, okay, which is a b term plus in absolute value 1, it goes to 0 as well, since limit bn is 0. Conclusion. The limit exists. So series converge. Okay. This proves the alternating series test, or the Leibniz test. Okay, of course, when we look at the previous example we had, we see that it obeys all the rules of the alternating series test. Let me give you some other examples. Okay. Now, in this case, clearly, okay, the general term changes sign with every increase in n, so it is alternating. Okay. The absolute value, 1 over logarithm n, decreases, and its limit is 0. Okay. So it converges by the alternating test. Okay. Likewise, the series are convergent by alternating series test. I want to consider a last example. Okay. The series minus 1 to the n over n squared and 1 to infinity also converge by alternating series test, since it is, okay, alternating, 1 over n squared goes to 0, and it's decreasing. Okay. I included the last example, okay, because all of these are convergent series by the alternating series test, but 3 has a specialty. That's to say, now, all 3 examples are convergent by alternating series test. Okay. But if we consider the absolute values, the sum of the absolute value should just start from 2, or the absolute value of minus 1 to the n over n, or n plus 1, okay? Or if we consider minus 1 to the n over square root n, then they are, okay, then these are all divergent. However, in example 3, the absolute value is still convergent. So, the behavior of these series, when we put the absolute value, okay, differ from each other. We have the following definition. Okay. If a series is convergent, okay, and with absolute value, okay, this series is convergent as well, then we call the original series absolutely convergent. Okay. Actually, this assumption is not necessary here, because if we know this, okay, if we know this is convergent, we already know this is convergent. However, here we call it absolutely convergent. On the other hand, okay, if the series is convergent, but the series with absolute value is divergent, then we call the series conditionally convergent. Okay. Thus, we have the following. A series clearly has two possibilities. It can be divergent or it can be convergent. If it's divergent, it is divergent. There is nothing to say, no more about it. If it's convergent, then we look at the absolute value version. If the absolute value version is also convergent, we call it absolutely convergent. Okay, that is, if also this is convergent. And we call it conditionally convergent if this is divergence. Okay. So this roughly explains the idea. First of all, a conditionally or absolutely convergent series is convergent. Okay. But everything differs on the absolute value versions. In the conditional case, it is divergent. In this case, it is convergent. Okay. Right. If we look at our previous examples, so the series where we had -1 to the n over logarithm n, starting from 2, is then conditionally convergent. Because when we put absolute value, it becomes divergent. Similarly, okay, the others, -1 to the n plus 1 over n, is conditionally convergent. But the last one, okay, even when we put absolute value, it is convergent. So this happens to be absolutely convergent. Okay. Note that when we consider, okay, the absolute convergence theorem, okay, it automatically says that the series without absolute value is convergent, but it in reality tells us that the series is absolutely convergent. So, a last remark, okay, in fact, okay, the absolute convergence theorem says that, okay, as a conclusion, the series is absolutely convergent. Okay. But the alternating series test does not say that the series is conditionally converged. But just convergent. We don't know about conditional or absolute convergence here. Okay, we have to check the series with the absolute value. Okay. From the above diagram, okay, we see that a convergent series can be split into two, conditional or absolute. Okay, but there is no thing like absolute divergence. Okay, a divergent series is divergent. There is no absolute or conditional divergence notion. Okay. And let me add the final statement here that note that the absolute convergence theorem and the alternating series test are both one-way tests. Okay. They never say a series is divergent. Okay. This looks like the nth term test, which is an one-way test, okay? But it never says convergent. Sometimes it says divergent. These are also tests which say that a series is sometimes convergent. So this is the point here. Well, about alternating series which satisfy the conditions of the alternating series test, okay, we have a very nice property following. Okay. Note the following. Of the tests we have covered so far, including the absolute convergence theorem, sorry, and the alternating series test, none of them tells us what the limit is, but just that there is a limit. So, all of the tests okay, that we considered, except the nth term test, okay, which tell us convergence, okay, do not say anything about is the limit. So they don't help us find the limit. They just tell us, okay, the limit has. Okay. But they tell us that there is a limit. Now, we already considered this before. I will repeat that. Okay. So, when a series is convergent, then we already noticed this before. There is an L value, which is the limit of the partial sum sequence, which we show by this symbolism. But we can write it as in this split form. Here, this is the limit. This is Sn. And Sn goes to L. Well, this means that this part happens to be the error term. If this is the exact limit value, this is an approximation. If n is larger, these two are near each other. So what remains on the right side, the error, must go to 0. When n goes to infinity. Okay. The question is, if we have a convergent series, this is the error. So the question is, can we estimate or control the error? Because if we want to say, okay, we don't know what L is, but we can calculate these SNs. Namely, by taking a large enough n, say take n3, add 3 terms. We can do that. It will be an approximation for L, but how large is the error? Now, this is a very difficult question in general. But in the case of alternating series, which satisfy the conditions of the alternating series test, this is very trivial. If the series is convergent by alternating series test, which means that it satisfies the conditions of AST, then error is easy to estimate. We have the following theorem. Okay. Let the series satisfy the conditions of the alternating series test. Hence, it's convergent. Okay. This means it's alternating. Absolute value of an decreases, and its limit is 0. Okay. Then, the error in question, that is, the error is less than the absolute value of the n plus first term if, okay, if we approximate L, that's the infinite sum, by Sn.